Hello, calculus students. This is Miss Orloff, and in this lesson, we're going to focus in on continuity of functions. And it seems pretty obvious when we see a graph if a function is continuous, but if we're just looking at a function, it might not always be so obvious. In calculus, it's extremely important if we know whether a function is continuous or not, because many of our theorems are only applied if we can confirm that a function is continuous. So let's begin. What makes a function continuous at a point? So if I think about this, and I'm going to on the side here sketch a graph of a function, and we're going to call this at C, and that's A. I'm hoping by now everybody understands that the limit of f of x exists because the limit from the right must equal the limit from the left, right? So for this function, I know that the limit as x approaches c equals a. But that does not mean that the function is continuous. Just because a limit exists doesn't mean it. We have one more element that must occur, and that piece that has to occur is that the value equals the limit. So let me write this out for you. We must know that f of c exists. So f of c means that in this case, I know f of c equals a. Okay, that has to exist. The next thing I need to know is that the limit as x approaches c of f of x exists. So yay. Why do I know that exists? I want to make a little side note here. This exists because the limit from the left of f of x equals the limit from the right of f of x. Beautiful. One major piece. Just because those two exist, if I go back to my diagram and get rid of this red point here, I mean, here's a scenario. The limit exists, f of c exists, but the function is not continuous. So just because they both exist, that is not good enough. What must happen is the limit as x approaches c of f of x must equal f of c. What you're going to find in an AP Calculus course is that you're going to have to show why, state why you know a function is continuous. What makes a function continuous? So what makes it discontinuous? So we're going to talk about 4 discontinuities. And honestly, we deal with 3. I rarely see the 4th. So the first type is an infinite discontinuity. And in this graph, we have an infinite discontinuity at x equals 2. In fact, that's a vertical asymptote. The next discontinuity I want to discuss is a removable discontinuity at x equals -4. And just a refresher, why is it removable? The original function has 2 domain restrictions, x equals 0, x cannot equal 0, and x cannot equal -4. I can create a new function by removing that domain restriction, and the functions aren't the same, but to the naked eye, the graphs are identical. The new function would plug up that hole, and that's why at x equals -4, we have a removable. This is where my limit exists, but I don't have a value at x equals -4. And number 1, the limit doesn't even exist. This next discontinuity is called a jump discontinuity. I'm going to abbreviate here. At x equals -2. What we know about this function is the limit does not exist at -2 because the left hand and the right hand limit do not equal. The value does exist, but it doesn't matter that the value exists. The limit does not, therefore we can't make them equal. This is not a great graph of this function, and it may be better to take a peek at it in your calculator. We know we have an issue at x equals 0, and this is called an oscillating discontinuity. It actually breaks right at that 0, and it's at x equals 0. You should try to graph this on your calculator. I do apologize, it's not the best hand-drawn graph. It is one we don't deal with often. So for the next part of our notes is we have to find each type of discontinuity. And so the first function is a rational function, which is a polynomial divided by a polynomial. And if we go ahead and we rewrite this, I see I have two domain restrictions. I know that x cannot equal -1, and I know x cannot equal -3. Those are going to cause discontinuities. I need to figure out which ones. I can rewrite what we call an extended function. We don't have to worry too much about understanding that this is called an extended function, which is not the same as f of x. It's almost identical. The graphs are, to the naked eye, are identical. They have the extended function has one less discontinuity, and this is why x equals -1 is a removable discontinuity. And x equals -3 is a infinite discontinuity. Sorry for my sloppy handwriting there. I'd like you to try B on your own by pausing the video. I have a hint. I want you to try to figure out, does the limit exist at 2? Because this is a piecewise function, and where a piecewise function breaks, we got to think about, well, does it break? We have to think about, is it a discontinuity? So I want you to think about, does the limit exist and does the value exist? Pause the video now and see if you can make that determination. So as soon as one of the criteria fails, I don't need to continue on. I know the limit doesn't exist because the limit from the left is 1 and the limit from the right is 2. I know that f of 2, which I did not need to check, is 2, but I want to make sure you understand that it comes from here because that's where we equal to. Don't need to check that because I've already failed to meet the criteria for continuity. And when the limit from the left doesn't equal the limit from the right, but they both equal a finite number, a constant, then I have a jump discontinuity at x equals 2. This is a popular question when I'm given this piecewise function and I have to find the value of a. Now we're going to assume a is a constant real number. So it's a real number. I should just say that right. And we have to find it to force it to be continuous. Well, let's think what meets the criteria. The limit from the left must equal the limit from the right. And I'll even take another, extend that a little bit more. First thing in limits is to plug a value in, to substitute. And if we get a constant, a finite number, we're done. But if we don't, we're not. So let's go ahead. Since this is x is less than 3, that's to the left. This is to the right. So if I was to take the limit, well, all I'm going to do is plug the value of x in. And I have, and I need to force the two sides to equal. And now this becomes a simple little algebra problem. So one thing that's different about calculus than other courses you have taken, I guess aside from geometry, is we have to justify, we have to state why we know something is true in words, but we never want to be like wordy. We don't want to go on and on and on and on. We want to be short and precise, okay? And so we have to determine or prove or show that these, or whether these functions are continuous. And then we have to state, hey, yeah, it is, but why do I know it is? Or no, I don't. So I want you to pause the video on number 1, and I want you to see if you can find some of the criteria. Find the limit at 1, if it exists, and find f of 1. So you can see in step 1, my checkpoint for 1, f of 1 equals 1. And checkpoint 2, in yellow, I found the limit as f of x approaches 1 from the left, and then I found it in blue is f of x approaches 1 from the right. They are both 1, so yay! The limit exists and it's 1. So guess what? Since the limit as x approaches 1 of f of x equals f of 1, and they all equal what? They all equal 1. Then f is continuous at x equals 1. Notice I didn't say it is continuous. I don't like the word it. What is it? I don't know. I'm specific. F is continuous. Where is it continuous? I only checked at 1. So I don't know that we need to do all of these, but what I'd like you to do, I want you to pause the video and I want you to determine, this might take you a few minutes, for number 2, 3, and 4. And then don't turn the video back on until you've checked all 3. And then we'll come back together and have a conversation. So let me look at number 2 again with you. I'm hoping you realize that f of 2 does not exist because neither one of these inequalities include 2. So because f of 2 doesn't exist, I don't need to check the other criteria. F of x is discontinuous at x equals 2. I probably should add in because f of 2 does not exist. And number 3, f of 2 equals 9. But in the second part, the limit does not exist because the limit from the right and left do not equal. Therefore, f of x is discontinuous at x equals 2 because the limit as x approaches 2 does not exist. Finally, a win. A number 4, f of 9 equals 3. The limit, I prove, equals 3 by showing that the limit, make sure I'm showing this, the limit from the left and the limit from the right equal. So I make a statement, I'm a closing statement. F of x is continuous at x equals 9 because the limit as x approaches 9 of f of x equals f of 9. That statement's required. If you want to add a little extra something, you could throw a woot woot or a smiley face or whatever makes you happy or celebrate this calculus, because calculus is fun. If a function, it should say, has a removable discontinuity at x equals a, would the limit exist at x equals a? And if the function has an infinite discontinuity at x equals a, would the limit exist at x equals a? So we talked about this earlier. A limit, I'm not saying is it continuous. Removable discontinuity. Check this out. This is a very generic graph. At x equals a, the limit from the left equals the limit from the right. So, yep, that limit can exist. What about an infinite discontinuity? So I think that's something we should talk about when we get together. Because if I can have a limit as x approaches some constant, and the left is infinity and the right is infinity, what do we say about that? Let's have that conversation in class. Take care, and I hope you all have a great night or day. whenever you are watching this.